Every single thought you have, every memory, every movement you make, it's all powered by this incredible storm of tiny electrical signals firing inside your body. So today, we're going to pull back the curtain on the fundamental spark that actually makes it all possible.
Just look at this for a second. It might seem kind of abstract, but what you're seeing is basically the origin story of your own consciousness. This isn't just some diagram in a textbook, it's the physical basis of you. So the big question is, how does this tiny little spark even work?
Well, to get how your brain talks to the rest of your body, you really have to understand the language it speaks. And it's not a language of words, right? It's a language of electricity. And the most basic fundamental word in that language is something called the action potential.
Okay, so let's meet the star of our show, the action potential. A lot of scientists just call it a spike, which is a perfect name, really, because it's this sharp, sudden burst of energy that carries a message. It's transient, meaning it's over in a flash, and it's all or nothing. And trust me, that part is absolutely crucial. We'll circle back to that in a bit.
But before any signal can fire, the neuron has to be ready to go. It's not just sitting around doing nothing. It's actively working, maintaining this very specific environment, just waiting for the trigger.
Probably the best way to think about a neuron that's just waiting around or at rest is to picture a tiny biological battery. Seriously, it's holding a charge, keeping up this difference in electrical potential between the inside and the outside. All that stored energy is the key to everything that's about to happen.
So, how does this little battery get its charge? Well, it's all about two key players, sodium ions and potassium ions. The cell works really hard to pump most of the positively charged sodium ions outside of itself, while at the same time it keeps more of the positively charged potassium ions inside. And the result of all that work? The inside of the cell ends up being just a little bit negative compared to the outside. That difference in charge is what we call the resting potential.
Okay, so the stage is set. The battery is all charged up. Now for the main event. What happens when the neuron actually decides to fire? Let me tell you, this is not a gentle ramp-up. It is a dramatic, explosive moment.
This is maybe the most important rule of the entire process. A stimulus has to be strong enough to cross a certain line, a threshold. If it does, the neuron fires with its full maximum strength, every single time. If it doesn't reach that line, absolutely nothing happens. It's just like a light switch. It's either all the way on or it's completely off. There is no in-between.
And this right here, this is the signature of that all-in event. This graph is like a slow-motion replay of the electrical drama unfolding inside that neuron. So let's break it down and trace the journey of that spike.
All right, here's the play-by-play. First, some kind of stimulus nudges the neuron right to its tipping point. That's the threshold. Then, bam, that's depolarization. Gates for sodium just fly open, and all that sodium that was waiting outside comes rushing in. This instantly flips the cell's charge from negative to positive. That's the huge upward spike. But just as quickly, the sodium gates slam shut and the potassium gates open. Now potassium rushes out, bringing the charge back down. That's repolarization. Finally, the potassium gates are just a little slow to close, which causes a brief dip where the cell gets extra negative before it finally resets itself.
Let's look at this shape again. That whole dramatic sequence we just talked about, the rush in, the rush out, the little overshoot, it all happens in just a few milliseconds, a couple of thousandths of a second. This right here is literally the speed of thought.
Now here's the real aha moment. The graph we just saw isn't some abstract idea. It's a direct measurement of what these tiny little protein gates are doing. You can see the pink sodium channels opening and closing, followed by the blue potassium channels. That rapid flow of ions through these channels, that is the electrical signal. It's a physical thing.
So, we've created a spark. Awesome. But how does that signal travel all the way from your brain to your big toe without just fizzling out along the way? Well, the neuron has a pretty brilliant solution for long-distance communication.
Okay, so there are basically two ways a nerve can send a signal. Up top, you see a slow, continuous wave moving along. But on the bottom, you see something much, much more efficient. The signal seems to magically leap across these huge gaps.
Here's the difference. Nerves that don't have an insulating sheath called myelin, they have to pass the signal along step by step, kind of like watching a firework fuse burn from one end to the other. It gets there, but it's slow. But nerves with that myelin sheath, that's the express train. The signal doesn't have to regenerate at every single point on the line. It just leaps from one gap in the insulation to the next. The result is just incredible. Up to 50 times faster communication.
And this amazing high-speed travel has a fantastic name, saltatory conduction. It actually comes from the Latin word saltare, which means to leap. And that's exactly what the nerve impulse is doing. It's literally leaping down the length of the nerve.
So we've been pretty deep in the weeds with ions and channels and gates, but let's zoom all the way out. Why does this tiny microscopic electrical event matter so much? It matters because of this. The incredible complexity of a memory, the nuance of an emotion, the precision of catching a ball, all of it is built from millions and millions of these super simple, identical, on or off sparks. The magic isn't in the spark itself, but in the unbelievable patterns and the timing of all their firings put together. And this isn't just theoretical stuff. We use this knowledge every day. By putting electrodes on the skin, doctors can actually listen in on these action potentials traveling to your muscles. It's called an EMG, and it can tell if nerve signals are slow or weak or maybe not there at all. It's a direct window into your body's electrical language, helping diagnose everything from a pinched nerve to more serious diseases.
So when you boil it all down, your entire nervous system is running on a kind of binary code. The spike is either on, that's a 1, or it's off, a 0. So you might wonder, how do you feel more pain or see a brighter light? It's not a bigger spike, it's just more spikes firing per second. The intensity of everything you experience is coded in the frequency of these simple all-or-nothing signals.
Which leaves us with a pretty wild thought to end on. Everything you are, your hopes, your fears, your dreams, your very sense of self, is written in this biological language of simple on or off electrical sparks. It's an elegant, powerful, and profoundly simple code that somehow creates infinite complexity. What does that make us?